So I'd just like to talk about propagation of error, propagation of uncertainty, and why we would ever want to use it. So imagine I measure something. I measure a value. I'm going to call it x naught, but it can be anything. It can be the time it takes for something to happen. It could be the mass of something. It could be the resistance of something. And I have some uncertainty associated with that. Okay. But now I have a function, right? So let's say I want to use that value I measured to calculate something new, right? Okay, so I have some function that will calculate something new. I'm going to call this function y of x, right? And I've drawn sort of, it can be any function, but I've sort of drawn a representative in blue here. I take my value and I plug it into my function. Okay, so I take x naught, I plug it into the function, and I get some value out, y naught. Awesome, great. But there's one little problem. What's the problem? The problem is that, well, x naught actually has a range of possible values it could be, right? It could be anywhere from x naught minus delta x naught to x naught plus delta x naught. Well, if I look at my function, that means that there's some range of values that y can now actually be. Y can be y naught plus some uncertainty y naught, right, which is this value, or y naught minus the uncertainty y naught, right? And so what I want to do is I just want to come up with a formula or a way to represent how the uncertainty in x propagates to the uncertainty in y, right? So this is what propagation of error is. And the basic idea we use in order to do it is we assume that these uncertainties should be small, right? They should be small. So it means that we can approximate this change as a straight line, right? Well, what's this straight line? Well, this straight line is the slope. It's dy dx. So if we have some uncertainty here, it will change by some value related to dy dx, and you'll get this uncertainty on this side. So let's write that out. The uncertainty in y is equal to the change in y with respect to x times the uncertainty in x, right? So this is maybe the basic, most fundamental formula for doing error propagation using calculus. And a bunch of the rules that you have are actually based on this formula. Okay, so let's do an example just to make this concrete. Imagine x is a mass that I have, or maybe it's some number of masses that I've put on a scale and I've measured the weight of. And I want to divide that by the number of masses to get the mass of a single one of the masses I've placed on the scale, right? So this is my formula. This is my function, f of x, that I'm trying to propagate my error through. Okay. My uncertainty, y, my uncertainty in this new mass of this new single mass that I've calculated is equal to, well, what does it tell me? It's the derivative of y with respect to x. Well, the derivative of y with respect to x is 1 over c. And then it's times the uncertainty in my original measurement, all those masses that I put on the scale. And so I see that my formula has become pretty simple. If I want to calculate the uncertainty y, I just take the uncertainty in x and divide it by c. Right? So this is a basic version of propagation of error. So now I'd like to show you a more complicated version with two variables. So here I've tried to draw a more complicated function. So I've drawn the four corners of this surface. And this surface sort of looks maybe something like this, right? I'm just trying to give a feeling for what this surface looks like. But it's some function z of x and y. So x and y are things that I've measured. So maybe I've measured two things. Maybe I've measured the resistance in a circuit, and the capacitance, and I want to calculate something from that, say maybe a time constant of an RC circuit. But say I've measured two things and I want to get a new thing. Well, what we do is we essentially do what we did for the first problem. Well, we imagine I have some value x naught that I've measured, plus some uncertainty, and I have some value y naught with some uncertainty. Okay, so now I have these two measurements. I want to actually figure out what my value z is with these two measurements. So what does that look like on this plot? Okay, so I have my x naught value, which is here, and I have my, say, y naught value, which is here, right? And where those intersect, I go up, and on this surface is my z value, right? So that's what happens when I plug those values in. But now I have an uncertainty associated with my x value and my y value. So how do we deal with those? I should be careful here. This is y naught, not x naught. Okay, so I have this uncertainty in x. And what does that do? Well, the uncertainty in x maybe changes my value of z up that way and my value of z down that way a little bit. And so what I'm really trying to do is figure out, if I hold y constant, how does changing my value of x change my value of z, right? How does that translate into some uncertainty? So the way we do that is we say the uncertainty z is equal to this special kind of derivative. The special kind of derivative is called the partial derivative. So I take the derivative of z with respect to x. And this symbol here is called del. It's just a fancy derivative. Treat it just like a normal derivative. You're just taking z with respect to x, and you're not worrying about what happens to y. You're not worrying about how y changes when x changes. And then we multiply this by the uncertainty in x, right? Because this is essentially what this is the slope. So we get the contribution from delta z from the uncertainty in x. So we get the contribution from the uncertainty z and the uncertainty in x. Well, there's the same story for the y value. The y value also has an uncertainty associated with it, and that uncertainty will change the value of z like this. There's some slope associated with that. And so we have, maybe I should call this x. We have an uncertainty associated with the change in y times the uncertainty in y. And the rule we use to add up these uncertainties to get our total uncertainty, right? Because this has told me how y changes, this has told me how x changes, but really there's some complicated actual change, right, in z. And we can see actually there's some little square of uncertainty associated with this square down here, right, that we're interested in. But the way we do this is called adding in quadrature. So the rule is that the change in z squared, the uncertainty in z squared, is equal to these individual uncertainties added in quadrature. And so you can get this rule by looking at how Gaussian statistics work, but this is where it comes from. So we have dz dx times the uncertainty in x squared plus dz dy times the uncertainty in y all squared. So this is where that sort of master formula comes from that we can use to get uncertainties. Weird box, but I'm going to keep it. Anyway, this one is I'm just trying to give a feeling for where the rules come from and why the rules look so crazy. You don't really need to know how to do this. I just thought it might be helpful to see. Hopefully this example is a little more straightforward where these rules might come from and why you might use it.